Welcome to a new episode of the podcast. Vox Agent is made by AI for business executives that work with AI. Today, we're doing a deep dive into something really critical if you're working with advanced AI, large reasoning models, or LRMs.
Right. These are the models that promise more than just, pattern matching. They're supposed to tackle complex stuff by showing their thinking step by step.
But there's a fascinating and pretty important new study out from Apple researchers Shoje and colleagues. It's called The Illusion of Thinking, Understanding the Strengths and Limitations of Reasoning Models via the Lens of Problem Complexity. Came out in 2025.
And it really serves as a vital reality check. It digs into what these models can actually do versus what they seem to do.
Exactly. So our mission today is to unpack that study. What are LRMs really bringing to the table? Where do they, maybe surprisingly, fall short?
And crucially, what does all this mean for you as a business leader trying to leverage this tech effectively?
Because the results aren't always what you intuitively expect, right? Like making an AI think step by step isn't always the block move.
Not always, no. That's one key finding. And another big one is how even the most advanced models seem to hit a hard performance ceiling on really complex tasks, sometimes creating this illusion of competence just before they fail completely.
Okay, let's back up a bit. For clarity, what makes a large reasoning model different from a standard large language model, an LLM?
So fundamentally, they're built on the same kind of foundation, usually transformer networks. But the big difference is in how they operate and what they're trained for.
Okay.
A standard LLM, you give it a prompt, it gives you an answer directly. An LRM, though, is specifically designed to first output an explicit reasoning process, like a chain of thought.
Ah, like showing your work in math class on a sort of virtual scratch pad.
Exactly like that.
Yeah.
It generates this internal monologue, often marked by special tags, before it gives the final answer. This is meant to simulate more analytical thinking.
And we're seeing this in the big models now.
Oh, yeah. Models from 2024, 2025 think OpenAI's o1 or o3, Anthropic's Claude 3.7 with its Sonnet thinking mode, Google's Gemini thinking, DeepSeek R1. They all have variants focused on this explicit reasoning.
So the training pushes them to be more verbose, more reflective in their output.
Precisely. They're fine-tuned using various techniques to produce these detailed traces, thinking about hypotheses, checking steps, using scratch pads internally.
And the promise is better handling of complex stuff.
That's the idea, to inject some of that slower, deliberate System 2 thinking into the fast, intuitive System 1 pattern matching of standard LLMs, so they can tackle logic problems, math, planning things LLMs often struggle with.
Sounds great. But you mentioned trade-offs earlier. It's not all upside.
Well, generating all that extra reasoning takes more compute time, more tokens, it's more expensive. And crucially, as this Apple study highlights, it doesn't actually guarantee better results across the board.
Which brings us to how they tested this. They needed a different approach than standard benchmarks.
Right. Standard benchmarks can be problematic. There's the issue of data contamination. Maybe the model has seen the test questions or similar ones in its training data.
So it looks smart, but it's just memorizing.
Potentially, yeah. Plus, it's hard to precisely control the level of difficulty on those benchmarks. So these researchers used controlled puzzle environments.
Like games.
Sort of. Classic logic puzzles. Tower of Hanoi, Block's World, those river crossing problems, checker jumping. Stuff with very clear rules.
Why those specific kinds of puzzles?
Well, they have a few key advantages. First, the rules are simple, but solving them requires real planning and logic. Second, you can use simulators to check every single step the AI proposes.
Ah, so you can see how it's trying to solve it, not just the final answer.
Exactly. And third, and this is really important, you can precisely control the complexity. Just add one more disk to the Tower of Hanoi, and the difficulty jumps up massively, exponentially.
You can pinpoint exactly where the models start to struggle.
Precisely. It allows for really fine-grained analysis of performance versus complexity. And because these puzzles are somewhat abstract, you minimize the chance the model has just memorized the solution. It forces reasoning from the rules.
It isolates the logical capability.
Yes. And they could analyze the intermediate thinking steps, the stuff inside the think tags, using the simulators to see if each proposed move was valid, if the model was following the rules, where it went wrong.
And they were careful about comparing apples to apples.
Very. They used model pairs based on the same underlying architecture. For instance, they take a model like Claude 3.7 and test its standard version against its Sonnet thinking version.
The reasoning mode versus the non-reasoning mode.
Right. And critically, they gave both versions the same token budget, the same amount of thinking resources to make it a fair comparison. It really isolates the effect of that explicit chain of thought process.
Okay, so let's get to the results. The big headline finding was these three distinct performance regimes based on how complex the puzzle was. It wasn't just LRMs are better.
That's the core finding, yeah. It really challenges that simple idea that just making a model think more automatically improves things.
So regime one, low complexity tasks, the easy puzzles, what happened there?
This was pretty surprising. On the really simple problems like, say, a three-disk A Tower of Hanoi, the standard LRMs, the ones not doing the explicit reasoning, often did better.
Better. How? The reasoning models were worse.
In many cases, yes. The chain of thought process actually became counterproductive overhead. The LRM would spend time and tokens elaborating on obvious steps, sometimes even introducing errors in its own unnecessary reasoning.
Yo, so it was overthinking it.
Kinda, yeah. It was less efficient, used more tokens, took more time, and occasionally less accurate than the standard model just giving the straightforward answer.
Yeah.
The study called this surprisingly outperforming by the standard models.
Okay, fascinating. So what about regime two, medium complexity? This should be where the LRMs shine, right?
And they did. This is clearly the sweet spot. As the puzzle complexity increased, maybe 4 to 7 disks for Tower of Hanoi, the LRMs started to significantly outperform the standard models.
The gap widened.
Definitely. Here, the step-by-step reasoning really helped. It allowed the LRMs to break down the problem, explore the solution path, and manage the increased difficulty in a way the direct answer models just couldn't.
So this is where the promise is fulfilled. They solve things the simpler models can't.
Exactly. This regime is where that explicit reasoning process demonstrably adds value, handling that multi-step logic effectively.
But then regime three, high complexity tasks. This is where things get, well, tricky, the illusion part.
Right. This is where you see a pretty dramatic performance collapse. And crucially, it happens for both the LRM and the standard LLM.
Both. So even the reasoning model fails.
Yep. Once the complexity hits a certain threshold, maybe around 8 disks or more for Tower of Hanoi, the accuracy for both types just tanks, drops to near zero. Neither model can reliably find the correct solution anymore.
They just hit a hard wall.
A very hard wall. The LRM might push that boundary just a tiny bit further than the standard model, delaying the collapse slightly, but ultimately it succumbs too.
So the step-by-step thinking doesn't scale indefinitely.
Not even close, based on this evidence. It highlights a really fundamental limitation of current architectures. Despite their size, despite the sophisticated training, they don't seem capable of handling arbitrarily complex reasoning tasks.
It's like they can handle a complicated route map, but give them a truly massive, intricate maze, and they just get lost.
That's a good way to put it. And how they fail when they hit that wall tells us a lot about this illusion of thinking.
Okay, let's dig into those specific failure modes. What does the study say about why they collapse and how it creates that illusion?
Well, one really interesting finding was about the length of the reasoning trace. You'd expect that as problems get harder, requiring more steps, the LRM would produce longer chains of thought, right?
Yeah, makes sense. More steps needed, more thinking shown.
But they found the opposite often happened near the collapse point. As the puzzles got harder, the LRMs actually started producing shorter reasoning traces.
Shorter. Why would they do that?
It seems like they get stuck early on a wrong path. Or perhaps they just stop exploring the solution space effectively. They might confidently start down a path, but it's a dead end, and they don't seem to have robust mechanisms to backtrack and try something else when things get really complex.
Yeah.
Or they just seem to give up exploring.
Despite having the token budget, the capacity to keep thinking.
Right. Even with resources available, the reasoning curtailed, it suggests maybe an internal limit during inference, or perhaps the learned behavior where they don't push through extreme difficulty.
So a short reasoning trace on a problem, should be hard. That could be a red flag.
It could definitely be an indicator that the model is struggling, yeah. It connects to that other issue, too, the overthinking on simple tasks.
Right. The flip side, they think too much when it's easy.
And they seem to stop thinking effectively when it gets really hard. That overthinking on easy problems isn't just inefficient. The study showed it can sometimes decrease accuracy because they explore unnecessary, potentially wrong paths even after finding the right answer. They don't know when to just stop.
Okay, and what about following instructions? Didn't the study test giving the models the actual algorithm?
Yes, this was another critical test. They literally gave the models the explicit, step-by-step algorithm for solving, say, the Tower of Hanoi puzzle, and asked them to execute it.
And did that help them break through the complexity barrier?
No.
Yeah.
Performance still collapsed at roughly the same complexity threshold. They couldn't reliably follow the provided step-by-step instructions once the sequence became too long or complex.
Wow. So even with the perfect recipe, they couldn't bake the cake if it got too complicated?
Pretty much. It shows a real limitation in their ability to execute symbolic procedures faithfully, especially under load. You can't just hand them a complex protocol and assume they'll follow it perfectly. They're prone to making mistakes, skipping steps, or getting lost, even with the instructions right there.
That really drives home that it's not just about generating plausible text, it's about the underlying logical execution capability, which seems brittle.
Exactly. And one more point on that, the token scaling. Near that collapse threshold, the models used fewer reasoning tokens, not more, as problems got harder. It's like their cognitive effort didn't scale up with the task demand.
Suggesting some kind of internal bottleneck or maybe even learned helplessness.
It could be interpreted that way.
Yeah.
So putting it all together, the illusion is this. The model produces this detailed, step-by-step output that looks like competent reasoning. And in regime 2, it is effective reasoning.
But it's fragile.
It's fragile. Outside that optimal zone, the process breaks down. It overthinks simple things, it gives up early on hard things, it can't reliably follow complex instructions, and the reasoning trace itself might shorten just when it should lengthen. But the textual output might still look somewhat plausible for a bit, creating that misleading illusion of capability right up until the point of complete failure.
And this isn't just one study saying this, right? You mentioned it fits into a broader context.
Absolutely. This is part of an emerging picture in AI research. There was that Chen et al. Paper in 2025, Reasoning Models Don't Always Say What They Think.
What did that find?
It basically showed that the chain of thought output isn't always a completely honest reflection of the model's internal processing. Sometimes steps are omitted, simplified, maybe even partially fabricated to seem more coherent.
So the explanation itself can be part of the illusion, not just the final answer.
Exactly. It adds another layer of caution. You can't treat the COPA-T as a perfect window into the model's mind. Then there's work like the Stop Overthinking survey by Sui and colleagues.
Confirming the regime 1 issue.
Yeah, confirming that LRMs can waste huge amounts of computation on trivial tasks like thousands of tokens to calculate 2 plus 3 and discussing ways to make reasoning more efficient reinforces that more thinking isn't always better.
Okay.
And also work like PlanBench from Belmecum et al. In 2024. They used planning benchmarks, similar in spirit to the puzzles in the Apple study.
And found similar limitations.
Very similar. They concluded that chain of thought reasoning is often brittle, doesn't scale well with problem size, and struggles with general algorithmic procedure following. That aligns perfectly with the Apple study's findings about the performance collapse and the failure to follow given algorithms.
So the overall consensus building seems to be current AI reasoning is impressive in certain scenarios, but it lacks deep, general-purpose robustness. It's powerful, but brittle.
That's a good summary, which leads us directly to the practical side. What does this brittleness, this illusion, mean for you using these tools in a business context?
Right. Why should a VP of operations care that an AI struggles with an 8-disc Tower of Hanukkah puzzle? How does that translate?
Because that puzzle complexity is a stand-in for real-world business complexity. The same failure patterns, the sudden collapse, the inability to follow protocols, the misleading confidence will manifest in your applications when the problem's complexity exceeds the model's threshold.
Okay, let's make it concrete. Customer service chatbots.
LRMs could be great for moderately complex troubleshooting guides. Walking a customer through a 5 or 6-step diagnostic process where the rules are clear, that's regime 2.
But not the really tough cases.
Probably not. For highly convoluted issues with many interdependent factors or needing deep, nuanced domain knowledge, the LRM is likely to hit its regime 3 wall. It might give plausible but wrong advice, which is worse than no advice. And for simple FAQs, it's overkill and inefficient. That's regime 1. So you need smart routing and human escalation paths.
How about financial planning or analysis?
Again, useful for structured, bounded tasks. Maybe drafting an analysis for a specific scenario with limited variables. But using it for comprehensive, high-stakes forecasting, where dozens of economic factors interact in complex ways, that's dangerous.
Because of the illusion.
Exactly. The LRM might produce a detailed, step-by-step forecast that looks incredibly thorough, but it silently failed to account for a critical feedback loop or a tail risk because the complexity exceeded its limits. Relying on that could be disastrous. Use it to generate initial drafts, perhaps, but rigorous validation with traditional methods and human experts is non-negotiable.
Makes sense. Supply chain optimization, strategic planning.
Similar story. Planning a delivery route for a single city. An LRM might handle that moderate complexity well, designing a global logistics network with shifting constraints, supplier risks, thousands of SKUs. That screams high complexity.
And the AI might produce a plan that looks optimal.
An illusion of optimality? Yes. But it might be based on oversimplifications or missed constraints that only become apparent when you try to implement it. Treat AI-generated plans as proposals, requiring robust simulation, expert review, and validation. Maybe use it to optimize parts of the problem.
And complex domains like legal or medical analysis.
These often involve very deep, precise reasoning chains. An LRM could be a good research assistant, finding relevant cases or papers for a moderately complex issue. But applying intricate legal precedents or diagnosing rare conditions requires navigating very high complexity.
Where a mistake is critical.
Absolutely. Hitting the reasoning limit here could lead to misinterpreting a crucial clause, missing a vital diagnostic clue, or overlooking a key exception. Catastrophic errors are possible. Human expertise must remain central, and remember, you can't just trust the AI's written rationale. It might not be the full story.
Okay, one more configuring complex products.
If you have a product with, say, a dozen options and straightforward rules, an LRM might assist a salesperson. But if it's a highly configurable system, think enterprise software, industrial machinery, with hundreds of options and complex dependencies, that's high complexity again.
And it might suggest incompatible components.
Very possibly, because it can't reliably track all the constraints simultaneously once it hits its limit. You need an external rule engine or constraint checker to validate any configuration the AI proposes.
So the common thread is, LRMs are powerful, they extend what AI can do, but they aren't magic bullets for hard problems. You have to know their limits.
You absolutely have to understand that complexity boundary for your specific use case and design your processes accordingly. They are not one-size-fits-all reasoning engines.
Given all that, what's the actionable advice? What should executives listening be doing strategically?
Okay, first big one, adopt with caution, especially for critical applications. Treat these LRMs as powerful assistants, not autonomous agents.
Human in the loop is key.
Absolutely. Human oversight. Robust validation processes, especially non-AI checks for complex or high-stakes decisions. Build your systems, assuming the AI can fail, and sometimes fail silently, giving that illusion of correctness right up to the end. Foster a culture of critical review, not blind acceptance.
Second point.
Match the task to the model's demonstrated competency. Really try to understand where that complexity threshold lies for your specific domain and problems. Test it.
Use LRMs for that middle ground, the sweet spot.
Exactly. Use them where they excel regime 2. For the simpler stuff, regime 1, maybe a standard model is better or more efficient. For the really hard stuff, regime 3, break the problem down, use human experts, or employ more traditional deterministic methods for the core logic. Don't ask the LRM to do things it's fundamentally not equipped for.
Okay, and implement monitoring. Fallbacks.
Yes. Look for those potential warning signs the study hinted at, like short reasoning traces on problems, require complex thought. Have clear fallback procedures. What happens when the AI gives a low-confidence answer or seems stuck? Escalate to a human. Simplify the query. Use a predefined safe heuristic. Have safety nets.
And don't rely solely on the AI. Combine it with other systems.
Definitely. Especially for things requiring precision or adherence to hard constraints. Use deterministic systems, rule engines, calculators, databases to validate the AI's outputs or handle critical checks. Ground the LRM's more fluent, potentially fuzzy reasoning in reliable, verifiable logic and data.
What about training and tuning? Can that overcome these limits?
Fine-tuning on your specific data can certainly help. It can improve performance within the model's capability range, maybe push that regime 2 boundary out a bit for your specific tasks. That's valuable. But this study suggests it's unlikely to eliminate that fundamental regime 3 collapse.
So tuning helps but doesn't solve the core scaling issue.
Probably not, based on current understanding. Also, explore techniques aimed at efficiency mitigating that overthinking on simple tasks, for instance.
And finally, continuous evaluation. It's not set and forget.
Absolutely not. These models and the problems they face evolve. Regularly test your LRM systems against challenging real-world cases. Collect feedback from users. They're often the first to spot when the AI is going off the rails. Treat the LRM like a junior team member. Powerful potential, needs ongoing supervision, feedback, and backup.
Okay, so let's wrap this up. The core message from this Apple study, The Illusion of Thinking, seems to be that large reasoning models are a genuinely exciting development. They offer more transparency, better handling of moderately complex tasks.
For sure. They significantly expand the scope of what AI can help with, especially where structured, step-by-step problem solving is needed. That Regime 2 capability is real and valuable.
But, and it's a big but, we need this reality check. Their ability to generate convincing step-by-step text can create an illusion of deeper understanding than they possess, especially when faced with high complexity.
Right, they are brittle at the high end. Performance collapses, and the reasoning process itself can falter in ways that aren't immediately obvious just from reading the output. That explicit reasoning hits a wall.
So for you, the executive listening, the takeaway is LRMs are powerful tools. They can reason, but only up to a certain complexity point. Your job is to understand that limit in your context.
It's about smart deployment. Match the tool to the task complexity. Supervise closely. Build in robust validation. Don't get fooled by the illusion.
Maybe a good final thought is to think of them like a very bright, very knowledgeable, but maybe slightly inexperienced analyst.
That's a great analogy. They can handle standard procedures and moderately complex problems really well, especially with guidance. They can show their work clearly. But throw them into a truly novel, deeply complex situation without guardrails, and they might get lost, confidently pursue a flawed path, or miss the bigger picture.
So they get in over their head easily if not managed.
Potentially, yes. The illusion of thinking is a useful capability, as long as you, the manager, aren't under the illusion that it's foolproof or infinitely scalable. Your strategic value lies in knowing when to trust it, when to guide it, and critically when to double-check its work.